Hey everyone, welcome to this another session of light, or I would say human eye, right? Same thing. Human eye perceives light, images, everything. So we are in a way studying light only. We have learned about refraction. You have done this. But you know what? Today we'll just move a level ahead. We'll talk about refraction and dispersion by prism. Prism is something which seems very fancy. In a way, it's just a glass slab, not exactly parallel, tilted like this. We'll talk about prisms, we'll talk about dispersions, we'll talk about colors, we'll talk about rainbows, we'll talk about refraction. So, first of all, understand this very clearly. Here, make your running notes and we'll just get this through. This difficult looking topic, will end it with a bang. Alright, ready? So, come on, let's start. First thing first, people who don't know about this, people who have missed this yet, the 17th July is the last date for the YTFREE code. The MLP sessions, the 3-session pack was free, right? But it is free only till 17th July if you use this YTFREE code. And please make sure you subscribe to it because everybody else has subscribed, alright? Please go ahead. You'll also understand in this there is the 2-teacher model, which is something you might have seen on the TV ads, on the YouTubes, right? Go ahead, check it out. One-to-one guidance from personal mentors, the live classes, and the best thing I would say is you can schedule your own timings for the class. That is a good thing, right? You have this much convenience in this. So go ahead, try it out because lot of you have already tried it. If you haven't done it already, do it because you know what? It's free. And something which is free, we should always try it, I would say. Okay, go ahead, try it out. Use the code YTFREE. The link in the description is shop.byju's.com. Click on that, use this code. The 399 will become free for you, right? 0. Fine, nice. So, let's talk about light. Let's talk about the splitting of light. And you know what? Let's talk about Newton. Is that a Newton? We know Newton from Newton's law of motion, right? But you know what? Newton has done a great deal of contribution in the world of optics as well. He was very interested in, learning about lights and colors. So what he did, one day he darkened his room. He just left a slit open somewhere so that sunlight can come with that slit, through that slit I would say, right? He used this glass looking thing which was like triangular. He kept it and what he witnessed, he saw colors of light. Like a rainbow, because that is somewhere we see naturally occurring colors of light, no? So he saw something like colors of light and he was amazed to see, wow, nice. It means light is something which can be broken down into different colors, huh? Nice. Something new he learned, right? So that's why this was, I would say, it's a colored spectrum which he found out and, we understood. A parallel looking glass slab does not do it, but you know what? This differently looking triangular glass slab does it. Okay, so let's understand this. What is this? So we have learned refraction through a glass slab till now, right? So let's start from somewhere we already are comfortable with. Let's start with refraction through a glass slab. What is? It's a rectangular slab, PQRS. Nice, easy. All right, now when light falls on the first interface, it goes from a rarer medium to a denser medium. So that's why it bends towards the normal. Okay, nice. Then at the second interface, it comes from denser to rarer medium. That's why it bends away from normal. That's also fine. But the first interface and the second interface, the bending towards normal on the first interface is getting cancelled out by the bending away from normal on the second interface, right? Getting this, right? Fine. So that's why what happens is the ray which emerged from the glass slab was actually parallel to the traced incident ray. If I trace the incident ray, you can see both of them are parallel. What is the angle between them? We have done this, by the way. What is the angle between these two lines? It is 0. Angle between two parallel lines is 0. We understand this, right? It's 0. Fine. Nice. So, what we can see? There is, angle is 0. But there is still some difference. What is the difference? If we just have a look at this, the difference is, there is some gap in between them, right? We call this the lateral displacement, okay? So this is what we say. The light ray is actually shifted. This is the lateral displacement between them. But angular wise, there is no displacement, right? Angle is 0. Incident ray and emergent ray, the angle is still 0. It's just they are displaced laterally. That's why this distance is what we call as lateral displacement. Fine. Nice. So emergent ray is parallel to direction of incident ray. We understand this. But what if I choose something like this? You know what? We say it a triangular prism. So this is what we call as a prism, okay? Yes. Let's say it's a glass prism. Materials can be there, right? Different optical materials can be there. Very common is glass. So what a prism looks like. It has this. I mean, if I just take a front view, it looks like a triangle, right? But you can see this isometric kind of view, right? So what do we see? It has a base. It has two sides like this, and this combined make a triangle looking thing, right? A 3D triangle, we can say, right? So how many triangular surfaces does it have? Think. How many triangular surfaces does it have? 1 or 2? So if we take a look from the front, it feels it has one surface. But you know what? If this you just shift like this, again it has one more triangular surface, no? So there are 2 triangular surfaces. Rectangular surfaces will be 3. Which rectangular surface? This one. This is what? This is a rectangular surface only, no? If I draw it like this for you, this is a rectangular surface. So this is 1, this is 2, and this is 3. So that's why 3 rectangular surfaces and 2 triangular surfaces, right? So this is what we call as a prism, okay? Right? Nice. So we understood this. This angle is what we call as the angle of prism. The angle between these 2 inclined surfaces, right? One is the base, that is just sorted, that is the resting place for the prism. But rest 2 surfaces, the angle between these 2 surfaces is what we call as the angle of prism. The angle between 2 lateral faces. Fine, okay? Nice. Now, what will happen if we replace the glass slab with a prism? So glass slab we have understood. Let's take a look what happens when you pass light through a prism. This is air, this is glass, this is air. I told you, most commonly we use glass prism only, right? This is the angle of prism. If I pass one light ray, I chose red, for example. This is the angle of incidence, right? Because this is the first interface. From air into glass, the light ray is entering. Fine. So what we can say, this is the angle of incidence. This is my normal, all right? What will happen? Rarer to denser medium, it is going to bend towards the normal. See, basics will always work, right? Don't just leave your basics for the fancy stuff. Basics will be there with you always. So take a look. Rarer to denser, it should bend towards normal. Means fine, it will bend towards normal. This is a bending towards normal, no? Angle of refraction is lesser than angle of incidence. We can see that. All right. Now, the light ray comes to the second interface. In this second interface, it is going from glass to air, denser to rarer. It will bend away from normal, definitely, right? So, let's draw a normal and see. This is angle of emergence. If this was the angle of incidence on the second surface, this is my angle of emergence. And yes, you can see angle of emergence is more than angle of incidence in this case, I would say, right? Fine. This is all basic still now. We understand this. Rarer to denser, denser to rarer, what will happen? All right. Now, what do we notice at least? In glass slab, the light was not bending angularly, I would say, right? It was going in the same direction. The angle between incident and emergent ray was 0. It's just they were shifted laterally, right? But you know what? Here it's different. What is the difference? If I trace the incident ray forward like this and the emergent ray, you will see this is my angle of deviation. What is deviation? How much it has deviated, right? Turned. That is what we call as deviation. And you can see this. Light ray without the prism would have gone straight like this. But now, where is it going? It is going like this. So that's why this is my turning of light, right? Light was supposed to go like this. Now it is emerging like this. So basically it has turned this much. And this is what we call as the angle of deviation. Got it? Is this term clear? Don't cram all these words. It's all lingo, right? You can understand this. So angle of deviation, representation wise, we say it with delta. This symbol is what we call as delta. All right. Nice. So yani ki, what we can say? Light bends in the case of prism, right? Correct? Fine. In a glass slab, it doesn't. Angle is 0. But here, it does. The angle is angle of deviation. So, kitna bending hota hai prism ke andar? Angle of deviation is the answer. Fine. Nice. Okay. So factors affecting angle of deviation. So this is something which I'll tell you today. I won't go into why or how, because today I don't want to confuse you on the very first day. Just listen to it. I'll tell you tricks to remember it, first of all. But someday, I'll explain you why and how also for this. Angle of deviation delta depends upon, first is refractive index of prism, right? Refractive index of prism. So this one is easy. Refractive index of prism. If more refractive index there, means light will bend more, refraction will be more. If refraction is more, means it will deviate also more, right? So ठीक है. Refractive index is something which is easy to understand. Nice. It depends on refractive index. Angle of prism also it depends on, right? Which angle? This angle, right? It depends on angle of prism also. Angle of incidence. It depends on angle of incidence also. What is this angle? Next is the color or wavelength of light. Now, this color or wavelength of light becomes important because every color, every wavelength does not bend equally. Why I'm saying this? Because we are going to talk about it, right? So, 4 factors. First one is very easy. Second is, I would say, angle of prism, which is something which is relatable to prism. Understand it or remember it. Angle of incidence is something which it also depends on. See, I can tell you the maths because very simple maths will give you an idea. Oh, that's how it depends. But you know what? Today we won't do it. Someday we'll do it, right? Then color or wavelength of light, right? What is the wavelength of light that is falling on the prism? It depends on that also. Okay, so now we have talked about 4 factors on which the deviation, the angle of deviation depends. Let's talk about the last one, color or wavelength of light. How does the angle of deviation vary with the color of incident light? You know what? It looks like the annual function thing, right? So yes, that's okay. So let's talk about colors and how they vary in terms of bending or passing themselves through prism, right? When you pass them through prism, what is different? Let's see. Color and deviation. Let's say this is the red color I have chosen, right? Okay. It went and then it emerged like this, and this was the angle of deviation for red. If this is violet, the angle of deviation is more. So should we remember it? Wait, you know what? You can remember it, but I don't want you to cram it. See, there's a difference between remembering and cramming. See, how do you remember? Color-wise, we have learned this. Bending of all wavelengths is not equal. Refractive index is higher for wavelengths which are lower. Okay, got it. So we have always, I have always told this to you. Red will actually bend least, not most, least. So red will bend the least because it has wavelength which is highest, at least in the visible spectrum. Violet will bend the most because it has wavelength which is least in the visible spectrum. All right. So red bends the least, violet bends the most. Understand it like this, okay? So that's why bending will be more for violet. Violet refracts more. This happens in glass slab also. Okay, we have to understand this. If it is a glass slab and you put a red light, it will refract less, and a violet light will refract more. That's true. Same concept is here, right? Bending, same thing, okay? So angle of deviation for violet is more than the angle of deviation for red. Means violet is bending more basically. Same thing. Whatever we have learned till now, same thing, right? It's just, you have to just rewire your learning from this, okay? Fine, nice. So why does the deviation vary? That is one question. All right, let's understand this. Not a difficult thing to do. Red and violet in air, or we can say vacuum, it's okay. Speed of all the colors is same. That is the speed of light we say, right? But what happens inside the glass? What doesn't change for that particular light? See, both of them have different frequencies and different wavelengths. That's true. Equally, they have same speed. So in air, all the light rays have same speed. What is different? Frequency is different. Wavelength is different. That's true. But inside the glass slab, what remains same? Frequency. What that color had before will remain same. This we understood. We have already learned about this, right? So if frequency for violet remains same, frequency for red also remains same, what changes? Lambda changes, right? Fine. Now, which of these light rays decreases most in terms of speed, right? Because speed reduces in denser medium. Red speed decreases, but violet speed decreases more, and that is exactly what this animation is trying to show you. It's a very slowed down version of the light where red light is slowing down, but violet is slowing down more. Okay, so that's something we need to understand. If violet is slowing down more, its lambda is decreasing more, right? Means it is bending more. In a way, we can say that. Okay, nice. So this is the reason. Air or red is the fastest and violet is the slowest in the visible spectrum inside a denser medium. All right. So that is why we get these colors, right? Different colors bend through different angles. And what is the spectrum? Spectrum is VIBGYOR, violet, indigo, blue, green, yellow, orange, red, right? So we have taken two extremes right now, violet and red. In between, every color will have different bending. So what do you see? Right now you can see red and violet, but in between it will be actually a band of colors. It's a spectrum which we'll see, right? So different colors bend through different angles and rays of each color emerge along different paths. Because white light is not a one color. It's a combination, right? And we have seen this experiment. Again, the person we started from, the name is there for this disc also. We call it the Newton's disc, right? White light is composed of all wavelengths. It has all these 7 colors, and when you rotate it very fast, it feels like it is just one single white color. So this is a proof, or it's a way of demonstrating that white light is a combination of these 7 spectrums. Okay, fine, nice. Let's come back to Newton. This phenomena of splitting of white light into colors is what we call as dispersion. Why does it happen? Because white light is a combination of 7 visible colors, 7 spectrums with different wavelength. And with least wavelength, you get more bending or more angle of deviation. With more wavelength, you get less angle of deviation, less bending. This is the whole scenario over here, right? So this is what we call as dispersion. Not a fancy name. Wherever you see splitting of white light is what we call as dispersion. So dispersion of light is splitting of white light into its constituent colors. Who did this? Newton did this, right? Spectrum is VIBGYOR, all right? So when white light passes through a prism, the violet bends the most and red bends the least. Fine. All right. Now, this is something which I have already told you. Violet has lesser wavelength compared to red, and that is the reason it bends more. All right. So this is a pictorial way of making a mind map in you. See, VIBGYOR, VIBGYOR. From violet, if you go towards red, the wavelength and speed increases inside the medium, inside the denser medium. First of all, just remind this, it's not like everywhere. Inside a denser medium, the wavelength and speed increases as you go from violet to red. But what decreases? The deviation decreases, right? So I would say this is one very important pictorial representation of that. You can remember it, right? So go ahead in your notebooks, make this kind of an arrow, write VIBGYOR, make these arrows, and you know what, remember it. And by the way, I'll give you the notes of this session on the Telegram channel. Don't worry about that. So recombination of white light. Is it possible to recombine? If let's say you have split the white light, is it like permanent? Is it done? Can you recombine it? Can you? Okay, just remember, take a clue from the glass slab. In glass slab, whatever kind of bending happened on the first interface, that bending got cancelled out on the second one, right? So I just need to figure out a way here on the first prism. What happened? If let's say light bent like this, I have to figure out a way to put something so that this light gets bent again like this. Which means all the colors which got bent like this, they will again bend like this, and it will become white light again. So in a way, you are thinking to use one more prism, but you know what? Inverted. And yes, if you do this combination, you will get another glass slab kind of thing, no? Doesn't it look like a glass slab? It does, no? Because this is what the glass slab was. I have just made its sides, it's like a parallelogram now. Okay, fine. So yes, this is how you can recombine. Here dispersion occurred, splitting, But this one has actually done the recombination and gave you white light again. So yes, it is possible to recombine the white light using this kind of an arrangement. It's a very common question in a lot of exams, right? So please make sure you understand properly. So people, let's summarize everything. Refraction through a prism, you have understood this, right? Dispersion of light, it's the splitting of white light, and recombination of light. We can do it, it's just you have to use an inverted prism. Fine. So people, there's a homework question for you. Have you observed dispersion in the nature around you? And write the examples of dispersion in the comment section. One is the most easiest answer, but I'm looking for creative answers. Go ahead, tell me in the chat what are different examples of dispersion you have seen in the nature. One, though I have told you in the session already. I'm looking for others. Okay, go ahead, give this answer, and please make sure you are a part of Telegram channel, because I'll give the notes of this session in that channel as well. Don't worry, right? So it's a good channel, be a part of it. You know, we have got you covered. I tell this every time, and I think you believe it, right? So we have got you covered. Make sure you like this video if you think this was helpful. You share it if you think it can be useful for someone else also. And subscribe it, because you know what? You don't want to miss anything. Whatever we are doing, it's for you, and it always be for you, right? Go ahead, subscribe channel, press the bell icon, and I'll see you again in the next session. Till then, take care. Bye-bye.